We'll record this guy right here. Would you shut the focus? So. We're going to be talking about capacitors, and I want to make sure that you guys are still up to speed here. So in your notes, you can answer this question. If a 200 microfarad capacitor is attached to a 12-volt power supply, how much charge will be stored in it? Go. Okay, what do we have? Who's got it? You got it? Check it. Cyrus, you got it? Andy? I'm not sure on the units. How'd you get it?
It's Q equals CV.
Q equals CV. There we go. He's not sure on the units. Microfarad volts is better than nothing. Microfarad volts. Let's see here. What is a farad again? Per volt. Right. Exactly. So we get 2,400 microcoulombs, or 2.4 times 10 to the minus third coulombs. 2.4 millicoulombs. And that's a kind of a standard amount of charge that you might expect to have on one of your circuit elements here.
Wait, so that's the same like 0.002
Wait, what's that C again? It's not coulombs.
Coulombs. Mm-hmm.
That one's coulombs?
This one is capacitance, that one's coulombs.
No, I know, okay. No, I'm talking about the beginning.
And I just apologize for physicists everywhere for using the same symbol for two things.
Can we change it up?
No.
Can we like put like a dot over top of it? Like something to identify it?
That makes a lot of sense here. It's really context that keeps the two sorted.
Wait, what are you talking about?
The dual use of capital C for coulombs and also capacitance, when the two really are directly related to one another. It's kind of like the use of the -1 for inverse functions and also for an exponent. Very unfortunate.
No, but I was gonna say, that C is used as a measurement and as a variable. It's not like a two different.
Right.
So
Right.
that's where it's kind of.
So it's slightly justifiable, but it's really confusing. Well, we want to ask a couple of questions here. The first thing that we want to talk about today is how much energy is stored in a charged capacitor. Now, we know something about energy. First of all, what type of energy are we talking about? Are we talking about potential or kinetic? Definitely potential, because we have energy that is stored up because of separation of charges. Where those charges are in relationship to one another, which is apart and they'd rather be together, so to speak. Don't anthropomorphize objects, they hate that. Because the charges are separated when they would prefer to be together, therefore there is going to be potential energy. And how much energy? Well, we know something about voltage and energy. We know that delta U is equal to Q delta V when we have a constant amount of charge. And so in problems that we worked earlier in this chapter, we took a charge like a proton or an electron or a charged dust particle, and we moved it around in a potential. And as it went from one to the other, then we stored up energy according to delta U equals Q delta V. Charging a capacitor is sort of like that, but with an important difference. And that is that the capacitor starts off uncharged with no E whatsoever. And as I pump charge into it, so this is the final state right here, but the initial state is like this, 0 volts, no charge. And as I pump charge into it, my voltage across the plates increases until we get to our final state where I have a final voltage of delta V right here, or we could just call it V, really. And we know that Q equals CV for that final state, right? So the question is, how much energy does it take to do that? It's not the same as taking all of my plus Q and moving it to this side right, or to this side right here, right? Because I don't have the same amount of charge during the entire process. It's not a constant amount of charge. So to get at that, gain an understanding of this, let's do a graph. We remember a similar kind of problem when we dealt with springs, right? Because work equals force times distance. But when I compress a spring, my force is continually changing because I have to push harder in order to make the spring compress more. F equals kx. And therefore, when I did work equals force times distance, I didn't just have kx times x as my amount of energy, but I had to do something involving area on a graph. Well, the same thing is going to be true here. If I take a graph of Q and V, then that graph, according to the equation Q equals CV, is going to have what kind of a shape? It's going to be linear. With what slope?
C.
C. And what Y-intercept? Or Q-intercept, as the case may be. 0. That's exactly right. Q equals CV is a straight line with a slope of C and a Q-intercept of 0, meaning that when V is 0, no voltage, then Q is 0 also, no charge. And that makes sense.
Wait,
Okay. So the slope is C. And now I picture changing, being in the process of charging up my capacitor. So the process of charging up the capacitor is the process of taking it from 0 volts up to a final voltage V, and in the process we stuff in to our capacitor, or we separate in our capacitor, a final charge of Q. Does that make sense to everybody? And what I guaranteed is that Q is equal to C times V. Now, let's imagine just a small change in voltage, and we'll call that small change in voltage dV. If you're in calculus, you immediately see where this is going. And I think you will agree with me that over that short dV, that the Q right here remains basically constant. It doesn't change by very much, especially if I make dV really small, something like 0.01 volts.
So this is like kind of the area.
That's right. So that the amount of energy stored up for this little process right here, and we'll call that delta U, is equal to the charge, which is approximately constant, times, do I want to do D's or deltas? I'll do D's. Times the change in voltage, just like that. Remembering that U is approximately constant. Well, if I now add up all of my DUs, I get the total energy understanding that Q is going to be increasing as we go out. So Q starts at 0, and it goes all the way up to CV by the time we get there. Okay? So one way to think about this is that the total amount of energy stored is the average charge times the whole voltage. And the average charge would be the average of Q and 0, which would be Q over 2. Right? So that would be one way to think about it. A second way to think about this, and a more mathematically rigorous way to think about it, would be to say that the total amount of energy stored is going to be the area underneath that curve right there. Or, if you're in calculus, it's going to be equal to the integral from 0 to V of charge CV times voltage dV.
I have a question.
And if you're in calculus, you can immediately compute that. But for the rest of us, let's take a look at the area, and then I'll come back to your question.
Okay.
So the area right here, then, is going to be what? Well, this is a fairly standard shape. What is the shape that we're looking at? It's a triangle. And so its area, which is the work done, is going to be 1/2 of base, which is the voltage, times the height. And that gives us the same result that we got by averaging. It is the average amount of charge stored in there while we're charging times the voltage right there. Or, if you allow me to replace Q with what it is, which is CV, then I get the more standard expression, which is 1/2 CV squared. Both of these are used, both of them are useful. And you calculus students have probably already mentally done the integral right here to get the exact same expression, right? Okay, your question.
Why doesn't the D's cancel out?
Great question. Because the D here is not a factor of D that's multiplied times V. This whole thing right here represents a small change in V. So this is one mathematical entity multiplied by another. It's Q times dV.
Okay, so then why do you get rid of the D when you go to the net, like down on one side? Right there.
Here?
No, over. The sum of Q, D, yeah. Why do you get rid of in front of the potential?
Here. Great question. So if we're thinking of the dU as a little tiny piece of the total amount of energy, then when I add up all of the pieces, what I'm really doing is adding up both sides here. So that when I add up the pieces of dU, what I get is the total amount of U.
Okay.
So if we think of energy as being kind of like money, then if we all go out to a fancy restaurant, take the Berkeley or something, then each of you is going to order a certain amount, right? And so if we call the amount of money M, then DM would be each individual's contribution to the bill. So you have dn1, dn2, dn3, dn4, etc. And we all add them all up, and what we get is the total amount of money that is spent for the entire. Does that make sense?
Yeah.
It's a totaling process. Great question. So coming back to our capacitor then, in the first slide, in the first problem, we wonder how much energy is stored in this capacitor as it stores this amount of charge. So let's ask and answer that question in a different color. How much energy is stored?
That's supposed to be a 9 to the negative 9.
Probably not. Where?
Mm,
Here?
yeah.
That's 3, minus 3. Micro is minus 6.
Oh,
So minus 3. How much energy is stored in this capacitor? And so we can immediately say that the amount of energy stored, U, is equal to either 1/2 QV or 1/2 CV squared. Take your pick. And either one is guaranteed to give me the same answer. So if I do 1/2 QV, because I've already computed the Q as 2.4 times 10 to the minus 3rd coulombs, and I have the V as 12 volts, then when I multiply these together, I get 1.2 times 10 to the minus 3rd coulombs times 12 volts, which is going to be 1.44 times 10 to the minus 2. Now what about my units? Well, obviously it's coulombs times volts, but what is a volt? One silence.
isn't it joules per coulomb?
It is joules per coulomb. That's exactly right. So that we get 1.2 times 1.44 times 10 to the minus 2 joules. Exactly.
And that's
So that's the 1/2 QV. If instead I had plugged in 1/2 CV squared,
you just.
that's right.
Why?
Notice that a farad volt squared is a, let's see here, coulomb per volt times volt squared. Which gives me coulomb volts, which again is joules.
What is your preferred method?
My preferred method, if I'm working a problem, is to use the given quantities just in case I messed up on the calculations. So here we're given the capacitance and the voltage, so it makes sense to me to use this so I can plug in what's given to me. Here I relied on a quantity that I computed in the previous section, which means that I have to rely on that quantity being accurately calculated, and it gives me just a little bit less certainty in my final answer. So in terms of being smart, I tend to try to use a formula that has all given quantities in it rather than computed quantities. But the difference there is one, right?
It just be maybe a rounding error or something like that.
Right.
Or if you close.
Or if you just screwed it up. Questions? Does this make sense to everybody? Cool. All right. The main show for today is networks of capacitors.
So capacitors link to other capacitors and other capacitors.
You got it.
That's awesome.
So what we're envisioning here, and as Andrew stated, is that we might have several capacitors hooked up to one another. Here's a power supply, plus V, and here are 3 capacitors, C1, C2, and C3, and all of these now form a network. And we might ask questions like, what is the total charge stored by the whole network? 4.
Would you have to add them up?
And we're going to find that out. It's not going to be trivial, but it will be very similar to that idea. what is the total charge stored by the whole network? Or what is the voltage drop across C3? In other words, we might ask questions about the whole network together, or we might ask questions about an individual component. And from an electrical engineering perspective, we might ask these questions because we might want to know, in the first case, how much charge can I expect to be stored in this network, right? I mean, the question is sort of obvious why you might want to know that. In the case of the second question, what's the voltage drop across C3, I might want to ask that question so that I can make sure I'm not exceeding the voltage rating on my capacitor.
Does it go down the more
Lest it
capacitors you
explode
have?
and go boom. What's that?
Does it go down the more capacitors you have? Or like higher?
Let me develop it, and I think you'll see. Now, when we connect these capacitors like this, there are going to be two main ways to connect them. And here, at this point, I've got to grab the eraser that fell. Two main ways to connect capacitors. The first way to connect capacitors is what's called a series connection. And in a series connection, where we have C1, C2 like this, you have one capacitor connected directly to the other with no branches coming off to the side. So the capacitors are connected at one end. If you'll allow me to call this one top and that bottom, and this top and that bottom, the top is connected to the bottom with no branches off to the side. In other words, there are no wires or other circuit elements attached in between.
So C1 will let us C2.
Correct, that's right. In series, just like Christmas lights in series, if one of them goes, then that whole part of the circuit is taken out. That's very good. Okay. The second main way that circuit elements can be connected is in parallel. Oops. And that's like what?
How they're starting to make the Christmas lights now.
Yeah. Yeah.
So if they don't.
And in a parallel connection, again, you have two capacitors, C1 and C2. But now, notice that both ends of the capacitors are connected to one another. And there do happen to be branches off to the side here, and those don't matter.
But what if both?
Then you get to replace them both.
So, but then, like, so in terms of like Christmas lights, I move the whole strip down. I guess.
So Christmas lights are a different kind of element. They're a resistor. And they work by getting hot enough so that they actually glow, right? I guess there are new style ones that are LEDs probably coming out. But they're probably pretty expensive. And so Christmas lights in series, if one of them goes, what that does is it takes out the ability of current to flow through the whole strip, right? If they're in parallel, then each one is directly connected to the power. So if one goes, then the rest can still go. That's how your household lights are wired, or should be wired.
You hope a wire.
Yeah. If they're connected in series, there can be more problems than one. So you should have lights in parallel, so that if one light bulb goes, then you replace that bulb, and that's it. Okay, so we have parallel connection. What makes these in parallel is that top and bottom, both ends, are connected. Everybody see the connection right there? Now we come back to our original network that I drew right here. You can see, no pun intended, that C2 and C3 are in series because they are connected at this point with no branches coming off to the sides. But they, well, that's it. They are connected here with no branches coming off to the sides. But C1 is not in series with C2. Yes, it is connected on this side, but there is a branching wire coming off right there. And that branching wire disrupts the series connection between the C1 and C2. Does that make sense? Likewise, C1 is not in series with C3 either. So C1 has no series, doesn't have any parallel connections. Is it connected at both points to either C2 or to C3? No, it's not. It's connected at this point to C2, it's connected at that point to C3. C1 is not in a parallel relationship or a series relationship to either one. That's okay. We're going to very quickly tomorrow acquire some tools for reducing C2 and C3 to an equivalent capacitor that will be in parallel with the other two. Okay? Now, I want to make some claims about parallel and series capacitors, and then that'll do for today. My claim is this. In series, capacitors share charge and, well, let's put it like this. Charge is shared. And voltages add together. Now, to get there, let me create a power supply and hook that up to two capacitors that are in series. Quick check the definition. Are these two in series? Are they connected at one end, no branches coming off? And this is plus V. As soon as I turn this power supply on, this capacitor is going to charge up and this capacitor is going to charge up. And the key is, because they are in series, there is just conductive wire between the two. And because there's conductive wire, if C1 had a higher charge than C2, then charge would flow until the two came to equilibrium. And if C2 had a higher charge than C1, then charge would flow until they came to equilibrium. And so because they have to be in equilibrium between these two, and there is no voltage forcing them to be in equilibrium in between. The voltage is all on the outside plates here.
So, like, kind of answer the questions that we have on homework.
Probably. Yeah, I don't remember that specific question, but there are several questions along those lines. And so because there is conductive wire in between these two, Q will be equal so that the capacitors are in equilibrium. Does that make sense to everybody? Okay. What about the voltages? Well, the voltages will add. Why? The voltages add because since they are connected at the one end but not at the other, then this spot right here has to be at V volts, and that spot right there has to be at 0 volts, which means that together these two have to drop from V all the way down to 0, which means that at whatever point this is, V1, right there, then the voltage difference here is V minus V1, and when I add that to the voltage difference there, which is V1 minus 0, look at that, I get V. So that the total voltage drop across each one, sorry, the individual voltage drop across each one must total up to V.
So it's be about 2 feet.
Possibly, but they might not be the same. So, I'd like to illustrate that. If you guys will all come up here, I have two capacitors in series. I had some problems with this in the other class. It turned out my circuit board was the faulty component. Let me do a little bit of reconfiguring. Now, if you compare the actual physical circuit that we have to the schematic, it's not obvious that these two are the same, right? Look at that. Look at that. Look at that. Look at that. It's like the Old Spice commercial. Look at me. Okay. So how do I know that these are the same? Because I look at the connections. If you take a look right here, all of the things in this row are connected to one another, and lo and behold, these two capacitors are in the same row. And nothing else is connected, which means these two are in series. If I look at the other connections, this guy is connected here and then out to, we call this the positive power bus, this red strip right here. This point is connected to everything in the same column. So when I run this jumper wire from here to here, I'm connecting this to that, which in turn is connected back to the positive end of my power supply. This blue line, this blue column, is called the negative power bus. And when I hook up the negative power bus to the negative part of the power supply, connect that to the rest of the circuit, that's connected also. Here I have a circuit lead that's just sort of jumping out to the middle of nowhere. See how that's not connected to anything on that end? That's just left over because I didn't feel like taking it out. This will actually have an undefined voltage at that point. Or if I connect to something else, then it will have a voltage really of zero, of the same as the negative power bus. So what do we have? We have one capacitor hooked up plus to minus, hooked up to the negative power bus, 0 volts at that end. Then it's connected to the second capacitor, which then hooks up to the plus V all the way back here. So the connections are the same as the connections in that diagram. Does that make sense to everybody? Okay, now let's turn it on and see what happens. Whoa! Just kidding. Don't you always wish?
Yes.
Yeah.
Forever.
You just don't want your face to be in one. Okay, so I'm going to first of all measure the voltage on the power supply. I'm going to do it indirectly by measuring what's coming into the power buses. Here and here. What do you get? 13.6. Okay. Now I claim that the total should be 13.6. So let me check that. 13.6. There you go. When I measure the individual components, here's my C1. 10.96. Please remember that. What do you got?
Negative 2.61.
What does the negative mean? I have it backwards.
2.611.
2.611. What is 2.611 plus 10.96? 13.5. What was the total? 13.6.
Well, 580.
Do they add up to the total?
Yeah.
Close enough. Close enough. And that should have happened in the other class. In the other class, this guy was acting a little hinky, and as a result, I was getting strange numbers that did not add up. This is the way it usually goes. To 3 or 4 sig figs, actually. We usually get very, very good results out of these capacitors and so on and so forth. A percentage error typically is going to be around 1% for these kinds of things, rather than the 10% error we often get from mechanics labs, which is nice.
You mean that 97% error?
Yeah, right, exactly. That's exactly it. So does everybody agree that voltages are going to add? Now I claimed also that charges were equal. Let's check that. You had 10.96 for this guy? Is that right?
10.96 for this one, 2.611 for this one.
Okay, well let's check. This was a 680 microfarad capacitor. and it had 10.96 volts. And this is a 1,000 microfarad capacitor at, what was it, 2.61 volts? Is that right? Okay. And so if I now say Q equals CV for each one of these, then for the C1, I get Q is equal to 680 microfarads times 10.96 volts.
Why did you say 6.8 times 10 to the negative 4?
I could do that.
Okay.
But I'm just going to express my result in microcoulombs at the end, so there you go. So 680 times 10.96 gives me 7,450 microcoulombs of charge on C1 for the total charge stored. Notice that I am not using the voltage of the power supply to make this computation. I'm using the measured voltage across that capacitor, because the Q stored in that capacitor is equal to the voltage drop across that capacitor times the capacitance of that capacitor. Does that make sense? Not of the power supply. Likewise, for C2, Q equals CV, which is going to be 2.61 microcoulombs times, sorry. 61 volts.
Technically it was 6.1.
This is interesting because we're not going to get nearly the same amount of charge here, right? So this guy ended up not being the same amount of charge as advertised. So we wonder what's up with that. And we suspect that perhaps one of these circuit elements doesn't have its rated capacitance like it used to. Some of these have been used for a fair amount, and they might not store as much charge as they used to. So we do not verify that our charges are in fact the same. This doesn't mean science is wrong necessarily. It just means that perhaps we need to check on the capacitance of our capacitors. Does that make sense to everybody? But we're happy with the voltages added. That was a good result. Okay, have a seat and we'll talk about parallel capacitors. For capacitors that are in parallel, I make two claims. I claim that the voltages are going to be the same and the charges add together.
So backwards.
Yes, very good. That's exactly right. That parallel has exactly the opposite logic of series. Voltages are the same and charges add together. And here's why. If I take a look at my two capacitors that are in parallel, and I take my two capacitors in parallel and hook them up to a power supply. Now to do that, I need to hook up my power supply like this, right? So here's my plus V, and here's C1, and here's C2. What I want you to notice is that because these guys are connected at both ends, it is necessary that they are going to have the exact same voltage at each end as the power supply does. So if this guy is plus V and that guy is 0,
Why
then
is it plus B and 0? Like,
remember the 0 is arbitrary. So I just chose this to be 0.
as in a point on a plane?
I mean, I could have chosen this to be minus V and that to be 0. I could have chosen this to be V over 2 and that minus V over 2. But all of that would be complicated, right? So I choose that to be ground. We call 0 volts, we call that ground. Okay? So here you can see that the voltage drop here has to be V minus 0, and the voltage drop here has to be V minus 0 as well. So the voltages are going to be the same because they are both equal to the voltage of whatever they're connected to. Why will the charges add? Well, what I mean by the charges adding is this. because they are at the same voltage, each one of them is going to have a different charge on it because Q has to equal CV. So we would say that Q1 here has to equal C1 times V, and Q2 here has to equal C2 times V. Right? Are you with me? Now, how much total charge is stored? Well, imagine that I take and I pull out one of these capacitors, and it's now charged up, right? And it has a charge of Q1 on it. And I pull out the other capacitor out of the circuit, it's charged up, and it's got a charge of Q2 on it. How much total charge do I have stored up in these two? Q1 plus Q2. That's it. How come that didn't work with the parallel capacitors, the series capacitors? Well, because if I take these guys and I pull them out of the circuit, right, then each one has a charge of Q, so I have a charge of Q here and a charge of Q here, but they don't have each one of them a voltage of V. They each have a different voltage, a lower voltage, because they were in series together. Okay. So where are we? Oh, that slide is out of order. Much better. All right. So we claim that the capacitors that are in series, in parallel, are going to have identical voltages. Let's test that. Come back to our measuring lab. I'm going to turn the power supply off before I go swapping out my capacitors. Generally speaking, hot swapping parts is a bad idea. And to make these in parallel, what I have to do is to get them both hooked up to the same connections on both ends. So I have to have this guy hooked up to that one on each end, like that. Does everybody see how this works out? There's a connection there, because these are all in the same row. And this is connected to the negative power bus. And these two are connected because they're in the same row and connected to the positive power bus. Okay? Turn this on. Do some voltage measuring. Turn it down on, yeah. And when I measure the power supply, what do I get? 13.56, remarkably stable it is. And when I measure this capacitor,
13.55.
when I measure this capacitor,
13.55.
and voila. We have the exact same voltage across each capacitor, identical to the voltage on the power supply.
Not want to turn it on.
Could do. What happens, just to give you a full sense of it, is that as soon as I turn it on, those capacitors charge up. It takes just a couple of nanoseconds to do that. And when those capacitors are fully charged, they hit an equilibrium state. So I could actually leave that on for the rest of time and nothing would happen to
Oh,
those
yeah.
capacitors.
They would get hot.
They don't get hot. They're charged, they're full, they're good. They are basically like stored up, like a spring that is storing up a certain amount of energy. Okay? Well, that's today's lesson, and we're out of time, so I'll see you tomorrow.